had a request for a little bit more practice and a little bit more help learning how to find p-values. And so I am making this little video to walk through a couple more examples. So first of all, just to remind us, the p-value is the probability of observing a sample statistic, so think about the sample statistic, as far from the hypothesized value in the direction of the alternative if the null hypothesis is true. So we're comparing our sample data to what we'd expect to see if the null hypothesis is true and deciding how consistent that sample data are with the null hypothesis. Because of this, smaller p-values are going to tell us that our data is less consistent with the null hypothesis and will be stronger evidence against the null hypothesis. Now, when we want to find the p-value, we're going to use our null hypothesis and our sample data to simulate the results showing the statistics that would occur by chance if the null hypothesis is true. That's what we call the randomization distribution. Then we decide which tail to use by looking at the alternative hypothesis. And finally, we are going to start the tail at the sample statistic from the original sample. And the p-value is going to be the proportion of dots in that randomization distribution that are in the tail or tails of the distribution beyond that sample statistic. So first example we'll take a look at. I've got a study that investigated whether informing hotel housekeepers that their work meets the Surgeon General's recommendations for activity would lead to a change in weight compared to a control group that were not informed. 75 hotel housekeepers were volunteered for the study, and they were randomly assigned to either be informed, that's the yes group in the STAT-key output, or not informed that their work met these criteria. All of the women were then followed over time, and the change in weight, the weight before the study versus after the study, was recorded. So before minus after, just to keep in mind, what this means is that positive means that they gained weight. Negative would mean that they lose weight. So we want to know, do the data provide strong evidence that the mean weight change was different between those who were informed and those who were not? Okay, so the first thing I'm going to do to formulate my hypotheses is just reflect on the type of variables I have. I have whether the woman was informed or not, which is categorical. And then I've got the weight change, which is quantitative. And so I'm going to be interested in a difference in means. So my null hypothesis is going to be that the difference in means is equal to 0, or that the two means are equal to each other. And the alternative hypothesis, I'm checking to see if it's different, doesn't indicate which direction. So mu1 minus mu2, there is a change. That means it's a not 0 difference, or that the two means are not equal to each other. Okay, so now we have our randomization distribution that's been given to us. Now in STAT-key, of course, I'd need to go into the randomization test for a difference in means. I'd put in my data in my original sample, which we can see is here, and then generate 1,000 samples were generated. Okay, so next I need to find my observed sample statistic. Now, since my parameter of interest is a difference in means, the original sample statistic that I'm going to use is the difference in means in the original sample. My sample statistic always comes from the original sample. So I've got x bar sub 1 minus x bar sub 2 equals 1.59. And just looking at it, I can see, remember, negative values were losing weight, and larger values were gaining weight. So what this means is that if I look at it, my no group has a higher mean, which means that they lost less weight than the yes group. So just to interpret this in context, in my sample, the informed group lost more weight. On average. Just thinking about what this number is telling me. Okay, so now that I know what my observed sample statistic is, 1.59, I'm going to use my randomization dot plot to find the p-value. First, I'm going to look and see if I'm doing a right-tailed, left-tailed, or two-tailed, because I have a not equal to in my alternative hypothesis. I know that I'm doing a two-tailed test. And I'm going to start my tail at my observed sample statistic. So 1.59 maybe is right here. I'd also have another tail down here. But when I'm finding the p-value, I'm focusing on the tail where the observed sample statistic was. And I'm figuring out what proportion of these 1,000 samples are in this tail. So I can see there are 3 dots out of 1,000 samples. So the proportion in this tail is going to be 0.003. Now, if I were working in StatKey, I wouldn't have to count the dots myself. StatKey would just put a little bubble up here, a little blue bubble that says 0.003, and it's going to put a little 0.003 on the other side for me. Right? But if I need to calculate it myself, that's how I do it. So because I've got a two-tailed test, I take the proportion of dots that I have in the one tail, 0.003, and I multiply it by 2 and get 0.006, and that is my p-value. Now, testing at a 5% level of significance, my alpha is 0.05. In this case, the p-value is smaller than that, so it's strong enough to reject the null hypothesis. The conclusion of the test, there's evidence that the amount of weight change differs between housekeepers informed that their work meets the guidelines and those who are not informed. The two-tailed test allowed me to detect a difference in either direction, but ultimately, if I'm going to try to decide whether to inform people of this or not, I'm going to want to know which direction the difference is in. And to think about that, I'm going to think about what I saw in the sample. In the sample, we saw that the informed people lost more weight on average. So that means that if I had done a one-tailed test in this direction, my p-value would have been even smaller, and I would also have had a statistically significant result. So I can say not only are they different, but that on average, housekeepers who are informed tend to lose more weight. So there's one example. Take a look at one more. Okay, so this study investigated whether women who are smokers have more difficulty when they want to become pregnant. And we're going to decide, do the data provide strong evidence that women who smoke are less likely to become pregnant than non-smoking women? Okay, so we've got two different variables here. We've got whether the person is a smoker or not, which is categorical. We've got whether they become pregnant or not, which is also categorical. So with two categorical variables, we're going to be interested in a difference in proportions as our parameter. So our null hypothesis is going to be, and we'll call P1 is going to be the smokers, and P2 is going to be the non-smokers. Okay, so we're looking to see if women who smoke are less likely, so that would mean that P1 is less than P2, or P1 minus P2 is less than 0, versus an alternative hypothesis that the two proportions are equal, or that the difference in the two proportions is equal to 0. All right, so we've got our randomization distribution that was simulated for us. We're going to use the original sample to figure out our sample statistic. We need to have P1 hat minus P2 hat, because we're estimating the difference in population proportions with a difference in sample proportions. We can see that the P hat for the smokers was 0.281. The P hat for the non-smokers was 0.379. And the difference in those proportions was negative 0.098. So that is our sample statistic. And again, I can take it from over here, my original sample. Now, I need to decide which tail I want, so I go to my alternative hypothesis. My alternative hypothesis is a less than, which means that I'm interested in a left tail, and I'm going to put that left tail at negative 0.098. So let's see, that's, we'll say, about here. Almost at negative 0.1. And we're going to figure out what proportion of the dots are out in this tail. Now again, if I use stat key, it would just pop up an answer for me. But because I am looking at the output, I need to count the dots myself. So 1, 2, 3, 4, 5, 6, 7, 8. Looks like there are 8 dots in that tail, divided by 500 total samples that were generated. So that's going to give me 0.016, and that is my p-value. And again, you can see up here that there are only 5,000 samples, even though it says right here that there are 1,000. There were really only 500. So again, our p-value, I don't need to multiply by 2 because it was only a left-tailed test, is 0.016. If I'm testing at a 5% level of significance, this p-value is small enough so I can reject the null hypothesis. there is strong evidence in favor of the alternative, which was that women who smoke are less likely to become pregnant than non-smokers. I hope this video is helpful as you're finishing up your studying for the second test. If you find you've got some questions, don't hesitate to come to my office hour tonight. It is from 7 to 8 p.m. Thank you.